This is Bob. Bob, turn around and say hi. Good boy. Bob did something with his life. He got himself a job. How did you get a job, Bob?
Um, I I asked for one, like I went up to the boss and I said, "Hey, can I have the job?" Oh, why is my name tag here? Let me leave it here. Yeah, yeah, yeah. Right, the name tag is supposed to be here. Um, yeah. So I just asked for one.
As you can see, Bob is extremely dumb. He's tasked with something right now in the job, and he can't even answer it. Bob, what's one plus one?
Um, I'm supposed to be able to know this. This is supposed to be a question. I'm supposed. Uh, I'll give a guess. I think it's 6, 7.
Bob decided to contact his friend, Nate Munget. Nate, what's one plus one?
This is a very easy question. As you obviously know, my handsome, beautiful stature. You see the hairline? My sunglasses. Yeah, 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 yeah. This question is very simple, and I'm very confidently able to say that 1 plus 1 is equal to 3. It's me, Nate, the goat of mathematics, and as you can see, the hairline is still there, as majestic as it's always been, and I'm here to help my friend Bob on this scenario. And he has the task of finding a new cylindrical shaped water well that has the least amount of surface area but can hold 54 pi centimeters cubed using optimization finding the minimum surface area. Slow down, holy. First we need to ask ourselves the question, what is optimization? And essentially, optimization, you got me, the goat. I'm here to explain it to you. Optimization is the process of making something perfect, functional, or effective by finding the minimum or maximum value of a function. Well, you may be wondering, what the hell does this definition got to do? And let's apply this definition to our question. So our question is this. And first, let's see whether or not this process is actually to make something perfect, functional, or effective. Well, the purpose is to find the most effective and practical surface area to reduce plastic. So yeah, it follows the first part of the definition. Now the second part of the definition, finding the minimum or maximum value of a function. Well, do we count? Can we design a function in it? Yes, and I'll show that to you. And the third thing, are we able to find a minimum maximum value? Well, the question is asking for a minimum surface area, so yes, we can obtain a minimum value. So the definition is true, and this question is optimization. And the reason why I just showed you this is because you may have a question on the IB math exam that you may not realize that's optimization, and you may have to go through this length of understanding whether or not this question asks for all 3 bits, and you can actually do all 3 bits, and then you should start approaching it like an optimization question. So let's do it. We've already identified the purpose, so the step 1 is already completed. Now let's do step 2, design a function. Well, how do we design a function? First, let's identify some formulas within the question. We obviously have volume, as they state that it can hold 54 pi centimeters cubed. So let's use the volume formula. Volume equals pi r squared times height. Now, obviously, our end result is surface area formula for a cylinder. So let's use the surface area formula for a cylinder, which is 2 pi r h plus 2 pi r squared equals surface area. Now, let's combine these two formulas that we have just identified into one singular function. And how do we do that? We do it like this. Personally, for me, I use height instead of radius, as radius is to the power of 2. and it's a lot more complicated, and height makes it more simply. You may be looking at my end result, and I have r to the power of -1, and it's like, what? Why did I do that? And in simplicity, it's going to help with the calculus in the very next step. So if you could ever leave an exponent or a variable to the power of negative something, you should very much do that instead of having it dividing. Alright, now let's do step 3. Obtain the minimum value, because obviously we need to get a minimum value. How do we do this? And you may be questioning, where am I supposed to do this? And if you did not watch our last video on local minimums, local maximums, turning points, and points of inflection, I really much recommend that you do that right now, because these concepts that we're about to cover is going to rely on you knowing these things. But as a quick short recap, we know the derivative tells us the slope of the function. Maximum value of a function has a slope of 0. Thus, if we set the derivative to 0, we can find the maximum or minimum value of what we're looking for, or in this case, the minimum surface area. So, let's do first find a minimum value. And this minimum value can be for any variable. And in this case, I found radius. So, I first did the derivative of ds over dr, got my radius value as r equals 3 or -3. Obviously, you cannot have a -3 radius, so I neglected that as one of my values. And now, before we calculate surface area, we still need to calculate height. And you may have other variables to calculate. So step 3.2 is find other variables' minimum value or maximum value if we're finding maximum surface area. Now we get height as 6, and then you plug that into your surface area formula, and you get 54 pi centimeters squared. Alright, this may seem simple enough. Now, it's your turn. Try out this question yourself. A toy company is designing a new toy, a cylindrical shaped toy with an opening at the top. They have only enough material to cover 96 pi centimeters squared. Find the radius and the height that maximize the volume and state the maximum volume. Well, I'll give you 3 seconds to pause the video and to take as much time as you need. Remember, this is a paper 1 question, so no calculator. If you have to use the calculator, you did something wrong. Okay, you have 3 seconds. 3, 2, 1. Here's the answer. Alright. The first, obviously, identify the purpose. Second step, design the function. And I kind of threw you a curveball here. I specifically say it's a cylindrical shaped toy with an opening at the top, right? So that means that there's no surface area at the top. So thus our expression is surface area equals 2 pi rh plus pi r squared, not 2 pi r squared. Alright, the rest is straightforward. If you get square root, you should still work with it, because it's paper 1, you should be able to work with square roots very easily. Alright, now let's move on to kinematics. Obviously, my friend Bob, I helped you. I basically did a huge major task for you in your job, and now it's time to tell you about kinematics. Physics students, you're going to like this quite a lot. However, do note that you have to approach kinematics in a mathematical mindset for IB physics students. So you cannot be using the kinematic equations that you're so familiar with. Alright, let's define what is kinematics. Kinematics is essentially the motion of an object, and we use different terms like distance, displacement, velocity, speed, and acceleration. You may be wondering, what do these terms even mean? Distance is straightforward. It's how far an object travels. Speed is how fast an object travels. It's measured between meters per second, kilometers per hour, and many more. It's essentially the distance divided by the time. And then acceleration is how fast or slow an object is speeding up, and it's measured between meters per second squared, kilometers per hour squared, and so on and so forth. It's just essentially the distance divided by time squared. Alright, let's first ask ourselves the question: what's the difference between our distance and displacement? And that's a really, really good question. Distance, we also know, it's how far an object travels. Displacement is how far apart the start point and the end point is for the objects. So let's take this example. Billy Bob III, he's a fabulous guy. You can all see because he's called Billy Bob III. He is right now beside this tree, and the tree doesn't have an apple, so he's kind of sad. So you want to go to the tree with the apple, but there's this wall blocking him. So what does he do? He goes around the wall, and that movement around the wall, up to the right of the wall and back down, that is his total distance. All right. However, his displacement is from the start point to the end point. His start point was to tree A, and his end point was to tree B. So his displacement is between those two. Now, you may be questioning, what's the difference between speed versus velocity? Well, here in this example, let's say that the total distance was 10 meters and the total time was 10 seconds. Thus, the speed is 1 meter per second. Sorry, I kind of made a mistake. It slips up a couple of times. But essentially, the speed is 1 meter per second as you took the total distance divided by the total time. Alright, now what about velocity? Well, let's say that the displacement was 2 meters. Alright? Now all we do to determine velocity, we take our total displacement and divide it by time. So 2 divided by 10 is 0.2. So the velocity is 0.2 meters per second, which is a lot more smaller than speed if you think about it. Now, let's combine our velocity, speed, distance, displacement, acceleration, and all into one singular diagram. This diagram is actually not quite known. I designed it myself in my grade 11 IB year, and you should I basically carried all of my kinematics. Alright, let's look at it like this. You have distance and displacement, right? Distance can only ever be positive because it's the total distance. You don't have vectors within it. And the reason why we have the m and s is because that's what it looks like on a graph. The y-axis shows meters and the x-axis shows seconds. And the distance is above the x-axis to showcase that distance is only positive. Meanwhile, displacement is below the x-axis to showcase that displacement can be also negative. Then let's look at speed and velocity. Speed, well, it's only ever positive. And on its y-axis, it shows meters per second. On the x-axis, it's seconds, or time. Velocity can be negative or positive, so that's why it's below the x-axis. Same for acceleration. Acceleration, if it's just dealing with distance and speed, it's only positive. But if acceleration is dealing with displacement and velocity, it can also be negative. Accelerations on the y-axis show meter per second squared, and on the x-axis it shows time or seconds. Now, you may be questioning, what are all these arrows for? To go from distance or displacement to speed and velocity, you need to get the derivative of it. And to go from speed or velocity to acceleration, you need to get the derivative of that. And then, if you want to go from acceleration to speed or velocity, you get the integral, and speed and velocity to distance and displacement, you get the integral. You may be looking at me, what the hell is an integral? And you will look at that later on. I won't explain integrals in this video, just as a side note. But that's how the diagram works. Alright, let's look at this question. A person runs every day on a straight line at the local park. One day, a handsome mathematician named Nate, if you know, he sounds like a handsome guy, honestly, modeled his run with this function. A. Find the velocity of a person at time t. B. At what time is the person at rest? And C. Determine when the person is moving forward and when it's moving backward. So the function is obviously st equals t cubed minus 6t squared plus 9t. S is we generally use s when we're talking about distance or, in this case, displacement. Alright, let's first tackle part A. Part A says find the velocity of the person at time t. Well, the velocity at time t is essentially the velocity time function. So if we just get, and we know from our diagram that in order to go from distance and displacement, we take the derivative of it. So thus we need to find the derivative of our function. Now let's find the derivative, and Vt equals 3t squared minus 12t plus 9. Now let's do question B. At what time is the person at rest? Well, when someone is at rest, that means their velocity is 0. So all we have to do is set our part A answer Vt equal to 0. And we just solve for t, and we get t as equal to 1 second and 3 seconds. Now, let's do part C. Sorry for the typo again. Determine when the person is moving forward and when it's moving backward. Think about it. If you're moving forward, your velocity is positive because your displacement is positive as well. But if you're moving backwards, your velocity is negative as your displacement is also negative. Alright? Now, let's apply our things. So essentially, the very first step is that we need to figure out at time 1 and 3, our velocities are at 0. However, before that, our velocity is either positive or negative. So we have to plug in the velocity values before and in between 1 to 3, and velocity after 4. There's many methods of trying to determine this, but here's how I did it. So I got velocity at 0 seconds and equals 9. That means before time t equals 1, velocity is positive, thus the person is moving forward. When we plug in 2 seconds a time between 1 and 3 seconds, our velocity is negative 3. So after t1 and before t equals 3, velocity is negative, thus the person is moving backwards. And then at velocity 4, at 4 seconds, velocity is equal to 9. After t equals 3, velocity is positive, thus the person is moving forward. Thus, we can state, therefore, the person is moving forward when time is less than 1 and greater than 3. And the person is moving backward when time is in between 1 and 3 seconds. Make sense? Alright. Now this is where I should talk to you. So, this is our last video. And generally I would say check out our next video, but because it's the last video, it's kind of sad. I'm gonna take off my sunglasses. Yeah. I just want to thank everyone for watching this process, being with us. It's such a glad to be there teaching you guys all, and this is the end of our gas project. We won't be posting any more videos, and if you need help or you have a question, feel free to ask me in the halls. But either way, this is Nate signing off for the last time. See ya.